All right, it's 1:03. I think it's a good time to start the lecture. Um, so hello everyone, welcome to the fourth lecture on the statistical foundation on reinforcement learning. Yeah, can someone tell me whether you guys can hear me okay?
Yep.
Okay, sounds good. Yeah, so we're gonna wrap up Markov decision processes today and move on to talk about some design principles in reinforcement learning algorithms while not worrying about exploration for now. Okay, so a few logistical notes. So the first homework, actually the first homework after homework 0. So this is the second homework, but it's called homework 1. Is officially released. So it is posted on the course website. And yeah, if you spot any issues and things that you find unclear, please let me know. And I'll update and I'll clarify the questions accordingly. Yeah, because this is the first time this course is run, so there might be things that I do not anticipate, and actually I do not have the full solutions yet. But as you work on the homework, if you run into issues that seems buggy, please let me know. Like it shouldn't, because many of the questions that I got from colleagues of my other institutions. But yeah, there are a couple of new things that I added to the homework. Yeah, another thing is that I've sent you on Piazza a Google Doc with a bunch of related papers to things that we cover in this course. So recall that the course project is a big part of our evaluation and also a big part of your full experience of course, which involves you reading a scientific paper in a reinforcement learning theory that's either recent or some classical papers on this topic. So most of the papers that I've picked, they're good papers. So they're definitely worthy of spending time to read. And I think if you do not have your own ideas on what to do for the project, you could consider browsing through that list of papers, look at the different topics, and then pick one that you like and then you find interesting, right? So often what happens when you read research papers is that research papers are written in a structured way. So you start by reading the abstract, and the abstract is already telling you what the main story is. If that got you intrigued, you could continue to read some part of the introduction to understand more details on the problem setup of and what the scientific problem that they're trying to solve, right? So in this way, you can get the too long don't read version of the paper before you decide to spend more time to work on that. Okay, so again, the basic project only requires you to read a recent scientific paper in this domain, and then later in the class, we will allocate some lecture time for different project group to present your findings. The project has milestones, so please refer back to the first lecture to see the detailed timelines for the items that are due for the project. For the proposal, all you need to do is to write half a page to 1 page document to tell me what is the paper that you're going to be reading, or what is this extension that you're going to be doing, and what the project team is, who are the people that you're going to be working with. All right, so you still have I think 2 weeks of time to form the project team and then pick a particular topic to work on. All right, and I'm happy to discuss with you if you have specific ideas on what to work on, and if you want to do something that's novel and like new scientific research, that's perfectly fine. But those projects are typically more and more ambitious. All right, so so as usual, we'll start with a recap. So last time we focused on Markov decision processes and the planning problem in Markov decision processes with a generative model. So the motivations are twofold. So first of all, computationally, assuming a generative model can sometimes deals with the cases when when computing and representing the entire transition kernel, which takes s squared times a space, is intractable in practice. And we only have some sampling oracles that can get us samples for any state action pairs and sample the next state in order one time, right? In this oracle time. So in this case, can we talk about how we can solve our MDP with access only to this sampling oracle? So and the hope is that we can get away with depending sublinearly in S. Subquadratically in S in terms of the number of times we have to query samples. Okay, and another motivation of studying this is that you can think about this MDP with generative models as a simplified version of the reinforcement learning where we assume away exploration. So in this case, we can explore any state action pairs as we want. And then the question is that what is the total number of samples that we need to collect in this case? So this is very similar to reinforcement learning because we do not know the underlying transition kernel, and we need to actually learn it by sampling from the transition dynamics. And we talk about one algorithm. So the simplest algorithm in this setting when we collect the data called model-based plugin estimator. The idea is basically to create an approximate MDP with the same state and action space, but with a P replaced with P hat. And this P hat is just a plugin estimator by simply using the empirical averages, they observe the frequency of the state transitions as a surrogate of the actual probability of the transition. So we know that this is unbiased estimator, and once we plug this into this approximate MDP, we assume the reward function is known, the discounting factor is the same, and the initial state distribution is known. So this is the only thing that's approximate. And once we plug this in, and then we can just take this to be the true transition, and then run value iteration or policy iterations to do planning, right? And then the question is about what is the optimal, what is the value of the optimal policy that you got from this MDP comparing to the actual optimal value function with respect to the true MDP when this P is and then we can talk about how many samples do we need to ensure this suboptimality gap is smaller than epsilon for all coordinates simultaneously. Okay, so this is straightforward algorithm, model-based algorithm. So in order to analyze this algorithm, we took two approaches. And before we took the first approach, we took a brief digression to learn about the concentration inequalities that's very typically used in statistical literature and in the analysis of machine learning algorithms. So these are really some of the fundamental building blocks of the theory of machine learning. So all these inequalities say something that's relatively straightforward, that the average converges to the mean. So both Hofstad's inequality and Bernstein's inequality are finite sample version of the law of large number, and a central limit theorem as these bounds are roughly the same as a Gaussian tails. So we're bounding the convergence of the mean to the convergence of the average to the expected value by bounding the amount of deviation, and then bounding the area under the curve in the tail of the probability distribution. So these are what these results mean. And the reason why they're called concentration is that because as the number of independent samples gets larger, this converges at a rate that's at 1 over square root of n to the population mean. And it concentrates, the measure concentrates around the center, and everything else becomes exponentially small. Okay, so that is why this is super useful, because it allows us to replace a random process and look into the property that happens with high probability in the randomized process using tools that are deterministic in terms of just these inequalities. Okay, and besides, the difference between the Hopkins inequality and Bernstein's inequality is that in Bernstein's inequality, we have a tighter bound when the leading term depends on the variance rather than the worst case bound of individual random variable, which sometimes improves things significantly when the random when the variance is substantially smaller than the largest possible value. Okay, and then we talk about the generalization of Hopkins inequality called McDiarmid inequality, where this f is a coordinate-wise Lipschitz function, and that takes x1 to xn as IID samples from some distributions, like independent samples from some distribution, and as long as f, the perturbation of f by changing one of these variable is bounded. If now I'm changing xj into xj prime arbitrarily, as long as the absolute value of this is bounded by cj, and maybe it is bounded by b, in a way that's independent to j, then we can essentially get the concentration of the expected value of this f. F converges to the expected value of this x at a rate that's exactly the same as the Hopkins inequality bound. Yeah, so that's McDiarmid inequality. And then like how do we like call multiple such inequality and make sure that they work together? We introduce this tool called union bound, which allows us to merge the multiple failure cases and by combining their failure probabilities. Okay, so these are some standard hammers that we use. So once we get over these concentration inequalities, we made use of these concentration inequality to analyze the sample complexity of the plugin estimator, like through two different approaches. The first approach uses the so-called simulation lemma, and then recall that we've proven this simulation lemma, and it has a very interpretable form, which says that if you consider an approximate MDP, the Q function of the approximate MDP for a given policy pi is close to the Q function of the original MDP, as long as P and P hat are close to each other. Okay, so it also depends on something else. So from the homework one, you will see that this is closely related to the occupancy measure. So in particular, every row of this matrix is an occupancy measure of this policy starting from the initial state as corresponding to that particular row, and so this is really the occupancy measure multiplied with the differences in the values. Okay, so what the simulation lemma does is that now we can say apply Holder's inequality to upper bound the gap for any pi. We can bound this by gamma 1 minus gamma and L infinity norm, L1 norm of P and P hat multiply with multiply with a maximum value of we had, and we know that this is smaller than 1 this is smaller than 1 over 1 minus gamma, which gives rise to, yeah, actually I think we don't have this, and this is smaller than gamma, 1 minus gamma p minus p hat 1. Okay, so this is what we call the uniform convergence because this is uniform over all policy pi, and as long as we can control with high probability that for all policy pi simultaneously their differences are small, then this helps us to counter the optimization bias. So notice that again the goal is to consider Q of pi star minus Q of pi hat star, and then we can add or remove the Q hat version of these, and then convert this into two applications of this uniform convergence bound. And the key issue is that this pi hat is actually data dependent, so we cannot naively use Hofstad's inequality. Therefore, we use uniform convergence. But luckily, this is uniform convergence, and then we can bound everything using 2 times that epsilon, which 2 times this is epsilon. Okay, so to bound to provide a high probability bound for this L1 norm of the estimated probability distribution. Yeah, I think I missed this max S and A, right? I missed this max S and A. So to bound this one norm error in the estimated probability distribution, we made use of the McDiarmid inequality, right? We made use of the McDiarmid inequality, and then we have a calculation of its expected value and bounding that expected value, and altogether they gave us the bound that we need. And then put everything together, we get the sample complexity bound that looks like the following, right? Which says that to achieve the epsilon suboptimality in the MDP planning problem, we need like this many samples suffices to get us there. Yeah, the catch is that this sample complexity bound still depends on S square, which can be prohibitively large, and it doesn't actually improve over the naive computational bound from the valuation itself. Okay, so we move beyond this this naive case and consider the second approach of bounding the sample complexity for the same algorithm. So the key realization is that we don't actually need the full uniform convergence over all policies. Instead, we only need to to bound the differences of the empirically optimal policy and that of its performance on the true MDP, right? So one handle that we have to solve that problem is this this so-called Q value amplification lemma. So for any Q, if we can show that this function is close to the Q star function for the MDP, then that implies that the greedy policy pi Q that takes this arbitrary Q function as an input is also a suboptimal is also like an epsilon suboptimal policy corresponding to the optimal policy. And the slight catch is that now we have this 1 over 1 minus gamma amplification factor that makes the error like slightly larger. Okay, so with this lemma, it reduces the problem to bounding the Q hat star and the Q star, which we can derive, and it satisfies this property. And once we have this, and the key idea is that we can collapse this inner product of this every row of this matrix with this V star, so that we're dealing with a univariate independent random variable, because notice that this V star is fixed and independent to the data, not data dependent. Yeah, so this is a key trick of saving a factor of S in the sample complexity, and then we can simply apply Hofstad's inequality for that. And once we do that, we get the overall sample complexity of this. So notice that the S square factor becomes S, and then we suffer slightly worse dependence on 1 over 1 minus gamma, the planning horizon, but we save this S factor in return. Okay, so neither of these approaches give us the optimal sample complexity, which has been shown to be this quantity. So the suboptimality from so the parameters that we are off from the second attempt is on this 1 minus gamma to the power of 6. So whereas the optimal sample complexity has a dependence on the planning horizon that's only cubic. Okay, so we didn't get to talk about how we can achieve this, but there are some ideas that you will be working on to move towards this goal by applying the different techniques that we have already learned. For instance, you'll be applying Bernstein inequality in homework 1 to and together with a Bellman equation for variance that you will derive in homework 1 to improve the dependence on 1 over 1 minus gamma. And moreover, like under some additional conditions, you can actually improve this so-called Q value amplification lemma to say that like you don't actually need this additional 1 over 1 minus gamma amplification in the error, which could further save you a factor of 1 over 1 minus gamma squared, right? So in total, these techniques together will give you the optimal sample complexity. Okay, so we won't be able to do this in the lecture, but hopefully you'll learn a few tricks by doing the homeworks. All right, so that was the recap of the last lecture. So today we're gonna be wrapping up the Markov decision processes. So there are a few like loosened knots that we didn't get to touch on. So in particular, there's this very useful performance difference lemma and the advantage decomposition that we didn't talk about, but we will be using this later when we get to the RL algorithms, the theoretical analysis. So we'll talk about it today, and then I'll talk about alternative formulations for the Markov decision processes. So sometimes those are more natural than the infinite horizon discounted MDPs. And after that, I'll talk about some design principles for reinforcement learning algorithms. Okay, that's a game plan for the remainder of today. Okay, if you have any burning questions, just feel free to stop me at any time or type into the chat directly, right? So I think you might have questions and thoughts about the projects. You could also type that into the chat box, and I may address that either during the break or at the end of today's lecture. All right, so the first thing that I wanted to talk about is this is from the section 1.6 of our textbook. So is to define so-called advantage function called a function of indexed by pi, right? So again, pi is the policy. So what does this advantage function say? It's really just a difference between the qpi function and vpi function. It talks about the advantage that you get. Suppose you take this action other than the action that would have been taken, other than just following policy pi, right? So this is an advantage that taking this action that will at this particular time point will give you over naively following the policy, right? So if we take pi to be pi star, then obviously then obviously this advantage function is always non-positive, because you cannot hope to beat the optimal policy by taking a different action other than the optimal policy. There might be two actions that are both optimal that gives you the same cumulative expected cumulative error reward in the end, but then that's saying that this inequality could have instances where equal sign is true. Okay, so why do we need this advantage function, right? So the nice thing about this advantage function is that it clearly describes the performance of two different policies. Let's say that you have policy pi and policy pi prime. Okay, and under the initial state distribution of mu, we have this identity that characterizes the difference in the performance of these two policies. Okay, so what does it say? It says that if you take the this is equal to the certain expected value of the advantage function of pi prime, and let's parse what this is saying. So first of all, what is S prime? What is this? This is d pi mu, right? So we've never really seen this before. But yeah, so you will have some fun with this in a homework 1. But let me define this first. So recall this part of this expression for d pi over mu. So this is a occupancy measure. This is the state occupancy measure, which we denoted as this new function under pi, right? So this is a measure. It's not a probability distribution, but if we rescale it by this constant multiplier 1 minus gamma, and then this can be converted into a valid probability distribution. So this d mu of pi is really the marginal distribution over the entire trajectory for you rolled out under pi for you to see state S. Okay, so we are taking the performance difference lemma says that the expected value of this advantage function as we roll in, right? So this is just say roll in to an infinite length trajectory and stop at a random location, roll in with policy pi, and then take the next action according to pi. Take action, stop at the random location, take action by pi, and then like you roll out. Roll out by pi prime, right? So when you roll out by pi prime, then you are comparing the two different versions that differ only by this particular action that you're taking at this random time point, right? So on the left that you of the difference, you take this particular action according to pi, right? And for the terms that you subtract, then you take this action already according to pi prime, right? So the performance difference lemma really quantifies the difference of the performance at every by saying that it is some average version of the advantage function by taking the inner product of this advantage function with a particular probability measure, right? And then we normalize it by making it slightly bigger over this factor. So to say it differently, the performance difference of these two policies, pi and pi prime, is the same as the occupancy measure of pi, state action occupancy measure of pi, and taking inner product with the advantage function of pi prime, right? So that gives you the performance difference. Okay, so there's a question in the chat saying that if we alter one step in the trajectory by taking a randomized action, not necessarily according to pi. I'm not sure whether this question is related to the advantage function itself or whether it is related to the performance difference lemma. But in the performance distance lemma, so you are comparing the trajectory that are that are like rolling in with pi to this random location, and then take actions by pi. So everything here is pi, and after that you take this action also by pi, and after that you take everything by pi prime, right? So you are comparing this with that you take roll in with pi, and then at this particular location you already switch to pi prime, right? And everything else is pi prime. Right, so this is what the performance difference lemma is saying. It's saying that these two different approaches that differs by only at this particular location by choosing a different policy, and then that completely describes this the performance difference of these two policies. Okay, so the proof of this is a couple of lines long, and let's look at it together. So in the first step, we're basically applying the definition of the value function, right? Yeah. First of all, it suffices to show this for every s. Then it applies for all distribution mu together, right? So for each s. For each initial state S, we can apply the definition of the first principle definition of this value function. So notice that we're using a slightly different indexing scheme that we're summing things from t equals to 0 to positive infinity, which changes this gamma to the power of t rather than the typical gamma to the power of t minus 1 that we used before. And the initial state will be S0 and A0 rather than S1 and A1. Yeah, but it's just a slight change of the notation that's being adopted by the AJKS book. Okay, so and then in the second step, we're applying in the second step, we're simply adding and removing this value function. Right, we're adding and removing the same thing. Okay, so notice that in this summation, we are in this summation we have R S0 A0 plus V pi S0 minus V pi S0, and then this is the first step, and gamma times R S1 A1 and plus V pi prime S1 minus V pi prime S1. So notice that this one is trailing behind, so we are subtracting V pi of S, and this got canceled out with this term. Okay, and then we can move this term together with a gamma factor to the previous line, right? But by simply regrouping this and then telescoping, and then the first line becomes R of S0 A0 plus gamma plus gamma of V pi prime S1, right? And then minus V pi prime S0, right? So that gives rise to do this for every line, that gives you this line. Right, it's by shifting this by the middle term by 1, and the first term got canceled with this one that's trailing behind, and then you get this formula, right? So this looks very much similar to Bellman equation, except that this st plus 1 is the random variable, but we are taking expectation in the outside. So by the law of total expectation, we can replace this with a conditional expectation. We can get rid of the randomness for this term first before we take the expectation over the entire trajectory, and then like this really becomes the definition of Q function on the pi prime. Okay, so by writing down this to be the Q function on the pi prime, then we construct the performance difference. Performance difference via this advantage function by its definition, and then that gives rise to, so the last term is really to use the definition of this state occupancy, right? And then this rescaling factor that makes the state state occupancy measure of a probability distribution. Okay, so I hope the proof of this lemma is clear. So that's all I wanted to talk about in the infinite horizon discounted Markov decision processes. And so now let's patch a couple of other things that we didn't get to cover in Markov decision processes. Let's talk about finite horizon MDPs. Okay, so in finite horizon MDPs, so what happens is that you typically do not have this discounting factor, but instead now that you are computing the cumulative reward that's undiscounted up to horizon H, right? So the so these are still the transitions, the transition kernels and the reward, and the transition kernel now is indexed by H. So it indicates the transition into SH from SH-1 and AH-1. And state and action spaces, they are the same. The reward distribution can also be time varying. So R of H, SH and AH is equal to the expected value of R of H when S of H is equal to SH and A of H is equal to AH. Okay, so it's just the more or less the same thing, except that now it's a finite horizon, and the goal of the planning problem in the finite horizon MDP is again to find epsilon optimal policy, right? And the epsilon optimal policy is determined is defined by let's define this value of a policy starting with mu to be the expected value of summation t from 1 to h R of h when everything is taken under this particular policy pipe. Okay, when the actions are taken when you draw out. So it's pretty straightforward extension to the infinite horizon MDP, and in some sense this makes more sense, right? So why should I discount the future reward? Like the reward is a reward. Why should I focus on today? So maybe my goal is to optimize the cumulative reward throughout the entire next 3 months and this window, and after that I'm gonna start a new new chapter of my life, and I don't really worry about what's gonna happen afterwards. Okay, so the thing about finite horizon Markov decision processes is that so there are some like inefficiencies in suppose you specify the transition like this. So this is what we call the non-stationary transitions, right? So we can specify the non-stationary transition, which is strictly more general because now the transition dynamics can actually change over time. Meanwhile, like sometimes they do not change over time, and even if they do not change over time, as we will see in the next slide, then there's some tricky business when we start to talk about Bellman equations and the value functions, v value function, the q value functions. So we say that this finite horizon MDP is stationary if p h s s prime s a is the same as p h prime s a for all h and h prime. Yeah, so and if it is non-stationary, then it's fully general. Then this transition dynamics can differ over time. Okay, so like I said just now, so even if this p functions and value of the transition functions and reward functions are stationary and time invariant, the corresponding value function and Q function are actually not. Why is that the case? Just imagine that you are already towards the end of this planning horizon, and maybe it takes 5 steps for you to get to a really high return state, but then you only have 3 steps left. Which means that you cannot possibly get to that high reward state anymore. So maybe you need to switch your policy to optimize for the remaining time that are needed. So maybe there's a second highest yielding reward state that you could actually get to within 3 days, and that would be your optimal course of actions. Yeah, in the infinite horizon case, you don't really have this situation because everything is the same. If you are currently at state S, then the future are all identical to you, no matter like which time is it, right? So if we define the value function, the V function and Q function, so they satisfy a set of Bellman equations. V pi t is equal to RT plus the undiscounted transition under pi at t and Vt plus 1. Okay, so this is about the V Bellman equation, and we can also write the Q Bellman equations. Okay, this is RT under pi, and all these are in R to the S. For the Q value function, this is equal to the transition. This is equal to the transition multiplied with Vt plus 1, right? This is also equal to R plus P tilde pi. Yeah, this indexed by T and Q. Sorry, I'm missing the pi here. Q pi T plus 1. And this is belonging to our state action, right? So these are the Bellman equations for all t from 1 to h. These are the Bellman equations for the finite horizon MDPs. Okay, so there was a question in the chat from one of the students asking about whether I can explain the reasoning for the point of why when P and R are stationary, then the V functions and Q function are not, right? So let's just consider the 3-state case: S1, S2, S3, and S2. I guess let's also add S4, right? So the state transition is like this, right? So once you get to S3, you transition back to S1, and once you get to S4, and then you also transition back to S1, right? And then whenever you get to, so all these arrows are actions. When you get to S4, you get a reward of 1, right? When you get to S3, you get a reward of 100. Okay, so this is a deterministic transition, and you start with S1, right? And let's say that the time horizon is h is equal to say 100, right? So typically, since S3 is the most valuable state, then the optimal actions will be to take this action to go to S2, and then take this action to go to S3. And then you visit S3, collect the reward, you are back to S3. So every 2 steps, you can get a reward of 100. All right. And then let's say that now we want to calculate the value function of h minus 1. So you only have 1 step left. And then this value function at S1, so what is it? So clearly, this value function is not the same as a value that you would have gotten. Suppose this this index is suppose this index is h-2, because if it is h-2, you can afford to take 2 steps to S3 and get a reward of 100. But you are currently at the last but one step, then you only have 1 action left. So the best that you can do is not to go to S3, which doesn't S2, which doesn't give you any reward, but maybe to transition to S4, which give you the reward of 1. Right. So this is saying that the optimal policy is non-stationary, is time varying. Also, the optimal value functions and the value functions in general, so they are different because I'm summing over a different number of rewards in the end. And so notice that this is a stationary transition, a stationary reward. Okay, so the key is that this is not the same as h-2. So this is likely to be, so V star of this is likely to be 1, and V star of h-2 is likely to be 100. Okay, so similarly, so the systems of Bellman equations for the Bellman optimality equation is also defined for every time step separately. So we will have this Vt star is equal to max of A R S A plus I guess the P max R of A plus P of PT and multiply with Qt plus 1 star, right? So that would be the Bellman optimality equations. Yeah, and yeah, this S prime is collapsed by this matrix vector matrix vector multiplication. Yeah, on the A, right? So S and A, and transition to this, and the Q. Yeah, I think VT star function is enough. S prime, sum over S prime. Okay, so that would be the Bellman optimality condition, and you can work out the Bellman optimality condition that depends on the time t for the Q function as well. Okay, so what about the structure to the policy? So in the infinite horizon MDPs, the key structure that we learned and we proved is that the policies are stationary. And actually, by stationary, we simultaneously mean that it is independent to the index t, and also memoryless in the sense that the policy only depends on the current state rather than everything that happened in the past. So the memoryless property is still the same for the finite horizon MDP. So due to the Markovian property, so the state variable itself also completely captures what's going to happen, capture the distribution of what's going to happen in the future. Therefore, it suffices to consider policies that only so the policy is pi t, so it only depends on the state that you observe at time t. Yeah, so for the optimal policy, there exists a deterministic memoryless optimal policy, but these policies are not stationary because they're indexed by t. They're memoryless, meaning that they depend only on the it's without loss of generality to consider the policy class that depends only on the state, but they are non-stationary. Because of the issues that we talked about just now, then depending on t, then the optimal policy could be very different. Okay. All right, so there are other aspects of the finite horizon Markov decision processes. So these are the performance different lemmas and how you define the advantage function in finite horizon MDPs. So it is still very similar, right? So instead of having this discounting factor and then the occupancy measure, so now the occupancy measure is for every horizon index separately. Right, and then we also define like an advantage function for every horizon, every time step h separately. So everything is quite intuitive, and there are also the equivalents of what we learned about the infinite horizon MDP, like simulation lemma, the linear program formulation, occupancy measures, and so on. And you can also try using the same technique to prove the sample complexity bound under the generative model setting. So in general, like the line of research on finite horizon MDPs is slightly more recent comparing to the infinite horizon MDPs, and some of the tight results are first derived for the finite horizon MDPs before they got applied and then generalized to infinite horizon MDPs. So there are things to be liked about the finite horizon setting. And there are also this slightly less clean cases, since all the useful functions of interest now are parameterized by the time index h. Okay, so you get to prove the corresponding simulation lemma in the last question of homework 1 about the finite horizon MDPs. All right, so I wanted to spend 2 slides to talk about the connections between finite horizon MDPs and infinite horizon MDPs, and how you can solve finite horizon MDPs using techniques for infinite horizon case and vice versa, right? So there are two-way reductions. They are not necessarily efficient, but sometimes they are. So first of all, from infinite horizon to finite horizon. So the idea is that due to the discounting factor, future rewards are exponentially small. So it suffices to consider a logarithmic factor, say logarithmic of 1 over, let's say that this is base gamma log 1 over epsilon over 1 over yeah, I guess this is not natural log. It suffices to consider this for the clipped version of the infinite horizon MDPs to have values that are uniformly bounded from the corresponding finite horizon version when h is chosen to be this, right? So once you clip that, then the entire tail due to the geometric series is smaller than 1. Sorry, it's smaller than epsilon, and then once you clip that, you can replace this with the same model for the finite horizon Markov decision processes and use the finite horizon algorithm to solve the infinite horizon problem approximately up to epsilon. And you can choose this epsilon to be arbitrarily small without substantially increasing the parameter h. The second thing is that you have to capture is to choose a time varying reward. So basically the reward now at time h would be defined as gamma to the reward at time h will be defined as gamma h minus 1 of the actual reward of SNA. Right, so this will be the parameters that you use in finite horizon MDPs, and that solves the infinite horizon MDP as well, right? So on the other hand, how do we reduce the finite horizon MDP to infinite horizon MDP? You can essentially like append a trivial state after as absorbing, and then it loops back to itself. So this is SH. So SH transition to H minus 1. So SH transition to the absorbing MDP all always, and the absorbing MDP keeps transitioning to itself with reward equals to 0. Right. So in this way, we can convert the the finite horizon MDP to an infinite horizon MDP, and as long as we set the discounting factor to gamma, it doesn't change the problem at all, right? So this becomes then the episodic version of the infinite horizon MDP. Okay, and the only difference is that now we are considering the state space to be the state space of time 1 union with the state space of time 2 union with the state space of time h, and then union with this singleton state that S absorbed. Okay, so that will be the joint state space in the infinite horizon setting. So there's also like a two-way reduction between the finite horizon MDPs with stationary transitions and non-stationary transition. So here's how it works. From stationary transition to non-stationary transition is quite straightforward. So basically, stationary transition would have the same state transition for that's time invariant. So this is equal to P H prime S SA, right? You can trivially make the parameter space larger and then just handle it using the non-stationary case while losing some statistical efficiency, right? If you add a further like affine constraints on the parameters, and then you do not even lose that statistical efficiency. Like the other way, like is more interesting. So suppose we have an oracle that solves the stationary MDP. So how can we apply that to the non-stationary finite horizon MDP? So the idea is like similar to what we had before. So we can consider the stationary MDP M with a state space being the union of S1 to SH, right? And then the transition kernel will be appended, like will also be extended to the action space is also extended. The transition kernels are extended, and H and mu. And we can add this additional structure that this transition kernel is in some sense a block diagonal form. So there are H blocks. Yeah. So when we add this additional constraint, then there are identical problems. So for these reasons, often when we solve problems in one of these settings, it implies results in terms of the sample complexity in another setting with some polynomial amplification in terms of the order of the polynomial, depending on the different problem-specific parameters. Even though it is still quite tricky to get the optimal dependence on everything for each individual setup, because they are typically different. All right. So lastly, for the there are other Markov decision processes settings that we will not be studying in this course. So there will be this infinite horizon average reward MDP, where the goal is to maximize the limit of h goes to infinity, the expected value of r sum of r t from 1 to h, right? So this is a so-called 1 over h. This is so-called average reward MDPs. Like in order for this problem to be well defined, like you typically need additional conditions, such as the ergodicity of the of the state transitions for all policies, and at least for some policies, and so on. So it's not a very clean setting, even though sometimes this is meaningful. Another thing that we won't be talking about is the indefinite horizon setting. So in this case, h is a random variable. So we talk about this frozen lake example, and when h is a random variable, then there's some tricky artifact that the reward design becomes more critical, because the agent can learn to make H to be larger or smaller in order to maximize its gain or minimize its losses. So for both the infinite horizon MDP and finite horizon MDPs, so the scaling and translation of the reward doesn't really change anything, and that was the reason why we can consider without loss of generality that R of SA is smaller than 0 and larger than 1, because that doesn't really change the problem at all. But for the indefinite horizon setting, this is not really the case. So let's illustrate that with this simple example. So we've seen this before. Your agent starts here, and this is a hole on this frozen lake, and this is some treasure treasure box, or just a bank of the lake that you want to get to. And whenever you get to either one of these two states, the game stops, and then you don't suffer any loss or incur any additional rewards. Okay, so the basic setting is that there's a time effect. So each step you always suffer a minus 0.04 penalty because the lake is frozen and you are very cold. You don't enjoy being in this environment. The state transitions are stochastic, and if you intend to move up, then there are some probabilities that you may not move up, but rather slide to both sides, either left or right. Okay, so this is a straightforward Markov decision process with well-defined state transitions and so on. So what is a reasonable policy here? What is a good optimal policy here? So clearly it depends on like this reward design. So let's say that if the reward is minus 0.04 as before, then let's say that even if you're here, right? Even if you're here, when you can potentially go up and take the shorter route, and then the optimal policy would prefer to go the longer route to stay on the safe side. Because yeah, if you risk going here, then there is a chance that you're gonna head this way and then drop into the hole just accidentally, right? So when the reward is designed to be minus 0.04, time effect is relatively small compared to the penalty of dropping into the ice hole, and then you will decide to get away from this as quickly as possible and take the longer route for you to get to the positive reward. On the other hand, suppose you replace this reward to be -2, then what all you want to do is to stop early. All you want to do is to end the game and end your torment in this in this hell, and to go die as soon as you can, right? So notice that when this is a design, then you will just jump into the hole right away to minimize the additional penalties that's coming from each step. Okay, so a question posted to you guys. So what if there's a positive reward for each step? I suppose this is like a nice park that you actually enjoy hanging around there. So what is the corresponding optimal policy? Anyone?
It goes towards the right, then up, then towards +1.
Not really. So when you get to +1, then you'll end the game, right? Then you no longer enjoy the positive reward.
Oh, I see. So it continues to move in the square type of fashion.
Yeah. So in this case, if the positive reward is sufficiently large, then the goal is for you to stay in this environment as long as possible. So chances are you will want to stay here, right? You'll want to stay here indefinitely, and then try moving towards this direction in each time. So that will be the optimal policy, because you will keep gaining like a little bit, and this is infinite horizon, and then the game will never end, and you'll get a positive infinity reward. Right, so this is just to illustrate that in some cases like this, when you have a indefinite, when the stopping time is a random variable, and things can get a little bit trickier. Yeah, so lastly, I wanted to talk about the partially observed MDP. So this was from one of the questions that one of the students asked in the first lecture. So the question student asked is about like Markov decision processes requires us to consider only the stationary policy. So how about the POMDP? Right? How about the partially observed MDP? So the setting is that you no longer observe the reward, but rather like the state, but rather you receive some random variables that's derived from the state, maybe one part of the state. So for POMDP, it's a significantly harder problem, but the key algorithm design is to essentially use a Bayes rule and derive the posterior distribution of your current state based on the entire history. One together with the observation at yeah, so you use your entire transcript and then to try to come up with some probability distribution over your current state, and that could be your how you choose your action. So even though it still depends on the entire history, so there is this summary statistic. This is a sufficient statistic of the entire history for you to make the rational decision going into the future, right? So this is a design principle for POMDP, and the key issue and the key challenge of POMDP is that computationally, like this is difficult to solve. Like getting the posterior distribution and finding the optimal policy is difficult. So we've seen that the MDP problem, it is a polynomial time algorithm. It is there's a strongly polynomial time algorithm by solving the interior point methods in the LP formulation. The POMDP, on the other hand, is p-space complete. Yeah, for those who are not familiar with a computational classes of different problems, so this is even harder than NP complete. For the learning problem, on the other hand, the MDP learning, we have polynomial sample complexity like always. That depends polynomially on all the input parameters. On the other hand, in the POMDP, so it really depends on what are the variables that you observe. So in many cases, the POMDP is not actually identifiable, that you cannot hope to recover the correct state or the underlying state transitions. You cannot learn the state transition at all. So all you can do is to predict the next observations, in which case there's a equivalent family of MDPs that gives rise to the same distribution for the sequence of actions that you observe. Okay, so both computationally and statistically, POMDP are significantly harder. Therefore, for this course, we're not going to cover POMDP. Yeah, it is a very useful and interesting setting, but it's just significantly harder beyond the scope of the course. Okay, yeah, we'll take 5 minutes break, actually 4 minutes break, and we'll resume at 2:15. And then I'll spend the remaining time to talk about some design principles for the reinforcement learning algorithm. So chances are I won't be able to finish, but that's fine, and I'll just resume the thread like next Monday. All right, see you guys in 4 minutes. All right, it is about time. Welcome back to the class. Yeah, if you have any questions regarding MDPs, and then I can answer them now, or I'll move to reinforcement learning. All right, yeah. So we've completed the section of the class on setting up the problem and understanding the mathematical model behind the planning problems of reinforcement learning. So we'll now go and talk about the more challenging problem of reinforcement learning, where the agent needs to learn online. So we'll start with algorithms, and we'll start with how what the pioneers of the field had been thinking when they designed some of the algorithms that became like popular nowadays, right? So one particular type of algorithm of interest are the MDP planning problems, where we use this dynamic programming algorithm for policy iterations and value iterations. Right, so these are the algorithms that we use. Then the policy iterations involving the policy evaluation and policy improvements. Right, you alternate between those two, and in policy evaluation, you solve a linear system of equation, and in policy improvement, you simply take the argmax of the Q function. Right, the value iteration simply simulates the Bellman optimality equations, and you repeat these processes until they converge. So the one design principle is to consider this algorithm and think like, how can we adapt this algorithm to cases where we do not actually have access to the transition kernel P, or have access to the reward, the expected reward function R. And in this case, what can we do? Okay, so these are called dynamic programming, and these are how it works, which we're already familiar with. But I wanted to point out that they are no longer valid in reinforcement learning, because none of these are actually known to us, right? So what can we do? So on this frozen lake example, so we know, like, if we deal with this as a pure reinforcement learning problem, then we know nothing about the reward. We also know nothing about the stopping condition and the final reward that you get when you hit those stopping condition. And then, like, we're asked what is a strategy to achieve the max reward. And in addition to that, like, we also do not see the transition dynamics, and actually those actions are not assigned with this semantic label, where we know that up is that my intention is to go up, down is the corresponding to my intention is to go down, right? So these actions are generic, and they are given to us, and we were given action 1, 2, 3, 4. So these are the only indices of these actions. We have no clue at any given state what this action is going to do, right? For instance, if the agent currently is here, then take action 1. So it could, like, potentially get you to this state directly, right? We cannot rule that out, because we do not know the underlying state transition. We do not know that this agent can only move to a sparse set of states in the state space, right? So I hope this example illustrates, like, why reinforcement learning is challenging, because we know nothing about the environment, nor do we know how to succeed in this environment a priori, and we want to learn everything from scratch. Okay, we want to learn the dynamics and learn the optimal policy, but maybe, like, if we can skip the dynamics and learn the policies directly. So there are several ideas that people had in mind when designing reinforcement learning algorithms. The first one is something that we have already talked about when dealing with the generative model setting. So the idea is that we can collect the data by running the agent to trials and errors, and then we can get a bunch of we can get a trajectory of how this agent interacts with the world. The agent will pick some actions at state 1, and then transition to state 2, collect immediate reward of this. And we can get a a bunch of these. Like these are coming from certain distribution that depends on both the agent's choices and the distribution of the nature. But like once the agent starts to explore, then we'll get like a bunch of data like this. Yeah, with this data, I guess the challenge is that comparing to the generative model setting is that this sequence of data, they're not really independent to each other, right? So they're coming from trajectories that the agent rolls out. Then the second data point actually depends on the first data point because it is S2, A2, S3, and R2. So they're strongly depending on each other because they even share the same random variable. Okay, but still, like if we just not worry about that, the good design principle is to plug in this data into the model estimator's parameters and estimate the P with P hat and estimate R with R hat. Right, and after that we can we can just create this approximate MDP and then use the same old value iteration policy iteration to try to address that. And we've seen that doing that with at least IID samples leads gives rise to pretty efficient learning that depends on 1 over epsilon square and then polynomial in all the other parameters of the system. Okay, so we can run dynamic programming by replacing this with empirical estimates, which we index canonically by adding a hat to these variables. Okay, like the one of the issues is that for is really exploration, right? So we can possibly like choose the actions randomly by choosing different actions and to just try different things. But the thing is, the Markov decision process is a long-term planning problem. So there are multiple steps. Often it requires us to choose a strategic sequence of actions in order to get to a particular state. And those particular states could be important in evaluating and identifying the optimal policy, right? In fact, as the time horizon gets longer, then the chances of randomly running into a state can be exponentially small if you simply take uniform random action. So what is an example of this? So let's consider state 1 and state 2, right? So if you take if you S1, S2, and let's consider the finite horizon MDP case to SH. If you take action A, then you will transition. So action 1, you will transition to S2. If you take action 2, it will transition you back to S1, right? If action 2, it will always transition you back to S1, right? So if you do this and then you take uniformly random actions, say P of A1 0.5, P of A2 is also equal to 0.5, then the probability for you to reach the final state SH, let's say maybe this SH is the only state that comes with non-negative reward. You get a reward of 1. In all the other cases when those states come with no reward at all, then the possibility for you to reach this state S is really exponentially small, right? So you have to be extremely lucky to continue to pick action A1 if you decide to randomly explore. Okay, so effective reinforcement learning algorithm needs to solve this trivial problem by coming up with a strategic sequence of actions to actually effectively explore the space. So we won't be able to talk about this today, but that will be a big part of the next part of the lecture. So after we talk about the algorithm design principles. right? So more generally, I think this model-based method is an algorithm design principle that's independent to how we collect the data, right? So once we have this data, the question in mind is that we wanted to somehow come up with an approximation of the policy of the dynamics P, the transition kernel P, and say we can use the function classes. Say we can choose P hat to be inside the function classes. This could be a neural network. Yeah, for those generative neural networks, say it could be GAN. It could be the mixture of Gaussian and so on. That gives us this conditional distribution approximation, right? So this P hat doesn't necessarily perfectly approximate P, or rather P might not be inside H. So there are approximation error somewhere. So I guess the simulation lemma would still apply, provided that this P hat is a valid probability distribution, right? So then you can create a synthetic MDP, and on this synthetic MDP, then you have the simulation lemma. And now it's just this term is not going to vanish, right? And the dependence on the final accuracy, like this approximation for that policy pi, and suppose you try to suppose you try to pick pi star hat is equal to arg max of q hat pi. So this pi hat star will not be maximizing q pi. On the other hand, like this approximation error, due to the fact that P is not in the policy and not in the function class, will get somehow amplified into the suboptimality of pi hat star. Okay. So this if is if P hat is a valid transition kernel, but error propagation might be tricky. Yeah, because you're not directly trying to approximate this Q function. You're approximating this Q function using the surrogate of approximating the model, right? So the error may propagate, and you may end up getting, say this is epsilon approximate. The corresponding impact on the suboptimality of the optimal policy on your synthetic or approximate MDP might be significantly more suboptimal compared to epsilon approx. Okay, so the second idea in the algorithm design for reinforcement learning is the so-called model-free reinforcement learning. So some of the questions that we could ask: do we need to really model the underlying dynamics? Can we somehow learn the Q functions directly? Right. So P is has S square A parameters. Yeah, let's for now consider the tabular setting. And how about Q? At least in the infinite horizon case, this Q Q only has S times A parameters. So there may be something that we can gain from here, even though from the previous analysis, like with the generative model setting. So even with the model-based approach, we don't necessarily need to approximate this transition kernel that well. So we can still get away with SA like a number of samples proportional to SA. So this saving is only motivational for this algorithm design. We could we could like one idea that we could do is to directly work with the policy iterations. And then generalizing it a little bit. So instead of doing the policy evaluation by solving the linear system of equation and knowing the actual Bellman equation, we can do this policy evaluation in other ways. And then follow this general algorithm design principle to alternate between policy evaluation and policy improvement. And similarly, we can do something like this for the better iteration. right? So we can do this without estimating the model, but rather directly estimating these steps of in the dynamic programming algorithm. Okay, so this is yet another algorithm design principle. We can use we can directly approximate Q hat from some given function class, some hypothesis class. Again, so this could be a deep neural network. And now the output of the deep neural network is no longer a probability distribution that you sample from, but rather it is a prediction of the value. So this hypothesis class contains functions. Contains functions that map from SA to a real value. And each individual element in this hypothesis class induce a particular policy class. So the policy class would be also indexed by the individual H in this hypothesis class. So it could be given by argmax of AS of H AS for all H in the hypothesis class, right? So this induces a corresponding policy class that is natural for this approximate value function class. Okay, so whenever we learn a good Q hat function, then we can use it to run, say, the greedy policy according to this policy class. Okay, so how do we do policy evaluation in the first place? Right, so let's follow this idea of policy iterations. It alternates between policy evaluation and policy improvement. If we do not know the transition dynamics, how can we estimate the performance of the given policy through interacting with the environment? The most straightforward idea is that I can just repeatedly run this policy, right? So now we have access to this environment. I can run this policy again and again and again. I can restart in the episodic case. If it is a purely infinite horizon case, I can start and then clip somewhere, right? I can like I discussed earlier. So clipping at an order that's proportional to 1/1 minus gamma is not going to change. It's not going to add a bias to my observed cumulative reward for that trajectory that significantly, right? So one idea is to use the so-called first visit MC. So let's say that we start this episode from S0. And we wanted to estimate the value function of V pi of S starting from state S. So what can we do? We basically find the first time we see S and then sum up all the subsequent rewards that we collect in this trajectory while running policy pi. So in this case, in this case, it is straightforward, and we can just add everything up. So 5 plus 1 minus 2 minus 3 gives us plus 2. So that's the first data point that we collect. Then we can start again and then keep playing this policy. So it's just a simple Monte Carlo, right? We can repeatedly play this policy and then collect independent samples that we can use to estimate the value of this policy. What does that give us? Since these are independent, we can average over the number of times we rerun, and then that gives us an estimator that approximates the actual value function. So how about discounting? Right? Suppose we are in the discounted setting, then the G1 would be G1 would be 0 plus gamma times 1 plus 0 plus gamma 3 times minus 2, and so on. So that will give me an estimate of the corresponding discounted reward. So once we if we actually want to maximize to do policy improvement, then it's insufficient for us to only estimate V pi through the through the policy evaluation that we talked about earlier. So we could alternatively estimate this QPi function, QPi function using, say, the first visit SA pair, right? So the first time we visit SA, and then we can keep track of all the subsequent rewards that we get, and then call that a random variable, and then over the multiple trajectories, then we can collect multiple samples for us to just use simple Monte Carlo to estimate QPi. Right. So once we have a QPi, then we can do the policy improvement steps by defining the new policy according to this greedy policy, and then like we alternate into the policy evaluation again by running this new policy and then try doing it again. Okay, so there could be exploration issues. There, like, in which case maybe we need to somehow randomize. Instead of doing the greedy policy, we need to run maybe the epsilon greedy policy, or use like other reward bonus kind of design to deterministically help the agent to explore. So this will be the topic of another time. But really the idea of Monte Carlo policy evaluation and policy optimization is to take advantage of this online access to this environment and to try things, to actually execute these policies. Like we could like apply the Bellman equations to estimate the Q function better using this formula, then by simply constructing the empirical approximate of all these quantities, right? So that helps us to do slightly better than having to visit all pairs of SA again and again, but rather only visit each S sufficiently for us to have good estimate of this VPi function. Yeah, so I guess there's also an online version of this Monte Carlo approach. So notice that we are simply getting all these trajectories and then taking the average. So trivially we can consider the online averaging. So we can consider that we output an estimator after observing every single trajectory. So after the trajectory 1, we're just outputting +2. After the trajectory 2, then we're outputting the average value of G1 and G2. And at the fourth iteration, after the fourth trajectory, we can output the average of all trajectories that we've observed so far, which has started from S at any given point, right? So you can write it in a slightly different way with this formula, with this update equation, and you can choose this update parameter to be one over the number of times that you have run into this particular state as ST. Right, so this is really ensure that V of ST is equal to 1 over n ST and sum over all cases from previously. Such that such that the starting point of this GT is equal to ST. Yeah, so we'll see why this formula would inspire us to consider the so-called temporal difference learning, because this is really the difference of what we currently believe the value of the state is and the new evidence that we observe from running experiments on the online environment. Okay, so the big idea of making the Monte Carlo approach more practical. So remember that the Monte Carlo approach is kind of a silly approach, right? So you need multiple trajectories, and you need a long time of exploration. You need to explore it for a long while before you can have a good estimate of the value function. And it is in some sense you are using the first principle definition of this V function, which is the expected value of the sum of the sum of individual immediate reward, rather than taking advantage of the recursive property of the Markov decision processes at all. Right, so it's kind of a silly approach that doesn't make use of the structure of the problem. So we shouldn't expect it to work very well in practice in terms of statistical efficiency. So if we the idea is then to combine the dynamic programming approach with the Monte Carlo approach and come up with an incremental update algorithm called temporal difference learning. So the Monte Carlo approach looks like this, the Monte Carlo approach looks like this. Now the iPad is running into a bit of a issue, but yeah, just bear with me with this animation across the multiple slides. So actually, like, all we need for this update equation is that G is an estimate. Maybe that's an independent estimate of the value function, right? So the issue of the Monte Carlo is that we can only observe one such estimate after finishing an entire episode. So the idea of TD learning is to somehow use a recursive definition, use the Bellman equation to estimate G in a slightly different way, right? So if we apply the Bellman equations, then we can get the expected value of G decomposes into the immediate reward that you can see right away after this step, and then the discounted future cumulative reward. Once you have this, if we estimate this, only need one step for us to estimate this part, right? The issue is that we don't actually have the true value function V pi, right? So what can we do? So that's saying that we can simply plug in what we currently believe what this V pi is, and use a so-called bootstrapping approach to update to update the parameter, right? So if we substitute this as G into this formula, and then it gives us the so-called temporal difference learning. So this is a temporal difference of the reward that you collect and the and what you believe is the rewards before you take that action. So this difference provides feedback for us to incrementally adjust our current belief of what the true value function starting from this state is. Okay, so how do we get this V? This is the so-called bootstrapping, where we're plugging in what we believe since R into the place where it should be the true value function, but we don't have the true value function. So the best thing that we can do is plug in what we think it is at the moment, right? So the hope is that once we do that, everything is gonna remain self-consistent, and then it is simulating this this Bellman equation iteratively, and if we choose this alpha to be sufficiently small, and it will eventually converge. Yeah, that's what they've shown asymptotically. So a little bit about the term bootstrap. Why are we calling this a bootstrap? It's coming from the novel by The Surprising Adventure of Byron Munchausen, which described like a whimsical story of someone picking up himself and then flying to the sky by pulling up his own bootstrap. So this is used in many cases in the scientific literature, in statistics. So this is a resampling method for estimating the confidence intervals without knowing much about the functions that you're dealing with. So in say computing systems, in operations, in operating systems, so this is about trying to automatically figure out the right configuration to interface the hardware to start your operating system. And in reinforcement learning, like Bootstrap really means the temporary difference learning. So in the Sutton and Bartle book, they commented that if there's one unique idea that's coming from the reinforcement learning literature, that's neither from the control literature nor from the statistical literature, then that is bootstrapping, right? So that is why this idea is central. It's at the very center of at least the development of reinforcement learning up to recent years. So we can also do temporary difference policy optimization. So there are two different approaches. One is called on-policy policy optimization. Is other called off-policy policy optimization. So on-policy like policy optimization called SARSA involves like always changing your the policy that you take your next action. Right, so you basically choose the next action according to some functions of this queue. It could be greedy, it could be epsilon greedy. So often you need to explore a little bit. And epsilon greedy means that you choose what you believe to be the optimal policy based on this value function Q with probability 1 minus epsilon. Otherwise, you choose an arbitrary other policy. You choose an arbitrary policy, say uniformly at random, right? So the key difference between SARSA and Q-learning is the SARSA is simulating the standard Bellman equation, whereas the Q-learning is simulating the Bellman optimality equation. Then Q-learning is off policy because it's off policy because it is it does not require the next action A prime to be chosen under Q at all. It could be arbitrary behavior policy that you are using to collect the data, whereas the Q learning will still try to update the Q function according to this formula. So according to this nonlinear updates. So both these two approaches under additional conditions in the tabular setting, and when alpha satisfy some condition that goes to 0, it converges asymptotically, and they are known to, like, from the experiment in practice, that they are substantially more data efficient than the Monte Carlo based approaches. And people are still like studying this algorithm and trying to establish how they work and why they are better than the Monte Carlo approaches by proving better and better regret bounds and sample complexity for these methods for identifying the near optimal policy. Okay, so I'm gonna so there are a couple of videos that I wanted to play, but maybe we can wait until the next week before I talk about them. Okay, so there are also some other interpretation of these temporal difference methods in terms of stochastic gradient methods. So there is an objective function that we can write down to derive the temporal difference updates. So I'll leave all those towards next Monday. But based on the algorithm and how they work mechanically, temporal difference learning has the advantage that it keeps updating your Q function many times throughout throughout the rollout of an algorithm. So the Monte Carlo within one single trajectory will only update the Q function once. On the other hand, the temporal difference learning will update the Q functions every time you receive an immediate reward. So by the time the MC update the function once with a good confidence, then TD has already made long progress towards optimizing this Q function and updating it towards the better and get it to be closer to the Q star function. Okay, so this is the same kind of improvement that you get by changing from gradient descent to stochastic gradient descent, where you incrementally update your parameters after randomly pick every individual data point. All right, so I guess I'll stop here. I'll cover the remainder part of the slides that I prepared today in the next lecture. And then in the next lecture, I'll finish the discussion on temporary difference learning, and then I'll talk about the policy gradient methods, and then hopefully prove this policy gradient theorem for you. So the policy gradient is a different approach for reinforcement learning. So the ideas of understanding this algorithm is to make sure that we do not do theory for the sake of doing theory, but also to understand how we design these algorithms and why this algorithm makes sense. And that helps to reinforce our intuition when we design algorithms and come up with provable guarantees for these algorithms. All right, so I'll end here. And thank you very much for coming. And don't forget to start on the homework 1 and then form your project group. Okay, thank you very much.